Good morning. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to take a look at section 11.5, which deals with E, which we will be talking about here. So let's see here. Here we go. All right. Think about the number pi. Pi is approximately 3.14. When is pi used? Pi is used in dealing with circles and spheres, circumference of a circle, the area of a circle, the volume of a sphere, the surface area of a sphere. Anytime you've got an object that has something in it that's round, pi is usually involved in calculating something to do with that object. All right. So pi, even though it's a symbol, stands for a number that is approximately 3.14, or a little more than 3. There is another number called E, which is approximately 2.72. So it's a bit less than 3. E is used when we're dealing with populations that are continuously increasing or decreasing. Think about, let's say, the population of Yakima County. Now, is this the way that it works, that nobody is born and nobody dies all year long, and then suddenly on December 31st, a bunch of people are born, a bunch of people die, and the population goes up or down? No, it's a continuous process, right? So when we're dealing with a population where it's growing or decaying continuously, the number E is involved in the calculations. Now, on your calculator, E is typically a second function key, and let's talk about that. So let's go back a minute and talk about log base 10, okay? Log base 10, which is called common log, is used quite frequently, so frequently that mathematicians have decided to use a shortcut notation. So they just use log, and the button on your calculator that you access says log, and the second function key is 10 to the x. Well, right near that log button, typically above or below it, there's another button that says ln, and this stands for natural log. Natural log is log base E. Base E is also used quite frequently, but since we've already got common log or log used up, they use the notation ln for natural log, which means log base E. Okay, and if you, on your calculator, the second function key of ln is e to the x, which will also help you to remember that log is log base 10 and ln is log base E. So again, we've got log or log base 10, the shortcut notation is log, and log base E, the shortcut notation is ln. All right. Later on, we'll be graphing some of that, but I want to do that lastly. So let's take a look at a formula for exponential growth or decay. But before we do that, in fact, let's go back to a formula that we used earlier in this chapter to calculate compound interest. If we have a certain amount of money invested at a certain rate over a certain period of time, and the interest is compounded yearly, so once for annually, twice, K would be 2 for semi-annually, quarterly, K is 4, monthly, K is 12, etc., etc. But what if we have a situation where the interest is compounded continuously? Well, then we would no longer use this formula. We would use a new formula, which is A equals PE to the RT power. Or think of the word PERT, P-E-R-T. There used to be a shampoo called PERT, but I don't know if it still is. But anyway, it's not P-E-R-T, it's P times E raised to the RT power. So we're going to use this formula when we're dealing with something where interest is compounded continuously, or we're talking about an increasing or decreasing exponential situation, a population that's growing or decaying exponentially. All right, so let's take a look at some problems involving this situation. So here's an example. It says, find A using the formula A equals PE to the RT power, given the following values of P, R, and T. Round to the nearest hundredth. So that would be to 2 decimal places. All right, this first problem, it says P is 5,000. R is 8%, which we'll rewrite as a non-percent number, as a decimal. And time is 20 years. Okay, so A equals 5,000 times E raised to the 0.08 times 20 years. Now, I have a couple of options. I can predetermine what 0.08 times 20 is and go from there, or I can just keep parentheses around that product and do it all at once. I'm going to go ahead and just do it all at once. So on my calculator, 5,000. Now, how am I going to access E? Again, that's the second button, the second function key of ln. So I've got 5,000, and then I'm going to push the second button or second function key of ln. When I do that, E raised to the parentheses shows up, at least in my calculator. Then I'll type in 0.08 times 20. I'll close that up and push equals, and I get 24765.16212. It said to round to the 100th place, so that would be here. The 2 would round down. So A is going to be 24,765.16. All right. Let's take a look at another example. In this example, the rate is going to be negative. So we've got, let's see here, P, the starting value is 15,895. R is negative 2%, which would be negative 0.02, and the time is 16 years. Now, since the rate is negative, the amount is going to be smaller at the end than it is at the beginning. So A equals 15,895 times E raised to the negative 0.02 times 16 power. And so again, let's see, 15,895, second function of ln, which gives me E raised to the power. Then I put negative 0.02 times 16 equals, I'm getting 11,542.13894. Again, rounding to the 100th place, the 8 would round up, so we get 11,542.14. All right, so there's that example. Next, it says, evaluate each expression without using a calculator. And it asks us to find the natural log of E squared. Now be careful. ln translates into log base E. So we have log base E of E squared. In other words, this E is a whole separate number from natural log. Okay, so we've got log base E of E squared. Well, let's say that that's equal to some unknown quantity that we'll call box. All right, so we now have a logarithmic equation that we can convert into an exponential equation, and that would be E to the box power equals E squared. Well, since the bases are the same and it's a one-to-one function, the box or the exponents are the same, so the box equals 2. So the natural log of E squared is 2. let's take a look at another one. The natural log of e to the fourth power. Well, this is the log base e of e to the fourth. We'll set that equal to some unknown. We'll change it to exponential form. So e to the box equals e to the fourth, the box equals 4. So the natural log of e squared is 2, the natural log of e to the fourth is 4. What do you think the natural log of e to the fifth is? If you guessed 5, you're correct. Okay, let's take a look at the natural log of 1 over e cubed. Well, that's log base e of, let's see, 1 over e cubed could be written as e to the negative 3 power. So that's equal to some unknown box. E to the box equals e to the negative 3, and the box equals negative 3. All right. How about this one? The natural log of the fourth root of e cubed. Well, that's log base e of e to the 3/4 power. Remember that the index becomes the denominator of the exponent. Okay, so that's going to be equal to 3/4. All right, let's use our calculator and find the natural log of 35.15. So now I'm not going to use the second function key. I don't want e to the x, I want ln, or natural log. So I'm going to push, first you have to turn the calculator on. I'll push the ln button and this shows up. Then I'll type in 35.15, 35.15, close up the parentheses and push equals. It said express all answers to 4 decimal places. So I've got 3.559624618. Let's see, 4 decimal places would be there. The 2 would round down. So the natural log of 35.15 is 3.5596. And let's do another one. The natural log of 0.675. So natural log of 0.675, close it up, equals negative 0.3930425888, which is negative 0.3930, because there's your 4th decimal place, and the 4 rounds down. How about the natural log of negative 10? So natural log negative 10, it says domain error. Remember, when we're taking the log, the base has to be positive but not equal to 1, and the amount we're taking the log of has to be positive as well. So you can't take the natural log of a negative number. Okay. Now it says solve each equation, express all answers to 4 decimal places. The natural log of x equals 1.4023. All right. Well, this isn't a logarithmic equation. So it's what? Log base e of x equals 1.4023. If we change this logarithmic equation into an exponential equation, we get e to the 1.4023 power equals x. So now in my calculator, I want to access that e to the x button. So second, ln, I push the second button and then the ln button, which gives me e to the parentheses. Then I put in 1.4023, close it up. Let's see, 1.4023, close it up, and I get 4.0645376661. And again, we're going to 4 decimal places, which is here, the 3 rounds down. So x is approximately 4.0645. Okay, so there's x. Let's see here. The natural log of x equals negative 0.28. So that means log base e of x equals negative 0.28. E to the negative 0.28 power equals x. Again, second ln gives me e to the parentheses power. I'm going to put in negative 0.28, close it up, push equals. We get 0.755783741. The 7 is the fourth decimal place, the 8 rounds up, so we get 0.7558 as our answer for x. Okay, we're going to look at some application problems or story problems. The directions here say continuous compound interest. So that's the introduction to the problem, continuous compound interest. That means we're going to be using the formula that contains E. All right, an initial investment of $2,000, so that's the principal, earns 8%, so that's the annual rate, 0.08, compounded continuously. All right, so that means we're going to be using E. What will the investment be worth in 15 years? So A equals $2,000 times E raised to the 0.08 times 15. Now, once again, we can predetermine what 0.08 times 15 is and go with that, or we can just do it all at once. I'm going to do it all at once. So I've got 2,000, and then second ln, so e to the, so I've got this. Okay, and then inside of there, 0.08 times 15, 0.08 times 15, close it up with a parentheses and push equals 6640.233845. And it said, let's see here. It doesn't really tell us where to round off, but since this is money, we would round off to the nearest cent, which would be the 100th column for the dollars. The 3 would round down. So $6,640.23. All right. Again, the key there was it was continuous. If instead of saying it grew continuously, it said compounded monthly, then we would use that A equals P times 1 plus R over K to the KT power, the other formula. Okay. Now, this next one says determining the previous balance. We're going to go backwards. They're going to tell us the ending amount, and we're going to use the formula to determine what we started with. Okay. It says an account now contains $3,610 and has been accumulating interest at 8% annual interest, compounded continuously. So there's that key word. Okay. How much was in the account 4 years ago? Okay. So the ending amount, the account now contains $3,610. The annual interest rate is 8% or 0.08, compounded continuously. How much was in the account 4 years ago? So we want the starting amount 4 years ago. Okay. So now we've got $3,610 equals P times E raised to the 0.08 times 4 power. In this case, I'm going to need to isolate P. So the next thing I'm going to do, I'm going to go ahead and predetermine what 0.08 times 4 is. 0.08 times 4. So that's going to be raised to the 0.32 power. Okay. Then I'm going to divide both sides by E to the 0.32 power. So that will give me P equals $3610 divided by e to the 0.32. So let's do that. 3610 divided by e to the 0.32 power. And I get 2621.398024. We're talking money, so we're going to round to the nearest hundredth of a dollar or the nearest cent. The 8 would round up. So we would have $2,621.40. That would be the starting amount in order to end up with this amount. Okay. Let's take a look at another problem. This says bed bugs. All right. It says, if not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. Oh my. If a colony currently has 50 bed bugs, how many will there be in 6 weeks? All right, so it's growing exponentially. It's a population. So we're going to be using A equals P times E to the RT power. Okay. The growth rate is 65% per week. So R equals 65%, which equals 0.65, and that's per week. The initial amount, it says we're starting with 50 bed bugs, and the time that goes by is 6 weeks. So notice this problem isn't in years, it's in weeks. The rate is given per week and the time is given in weeks. So A equals 50 times E raised to the 0.65 times 6. Be careful converting the percent, okay? 65% is 0.65. So I'm going to put all this into the calculator at once. 50, and then second ln, so E to the, and then I'm going to put in 0.65 times 6, 0.65 times 6, close it up and push equals 2470.122455. Since this is a living creature, we'll round off to the nearest whole bed bug. So it would be approximately 2,470 bed bugs. Doesn't that make you want to go lay down for a nap? Okay. Let's take a look at another example. This problem, it starts out by saying the Big Easy, which I believe is referring to New Orleans. It says New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, how long will it take for its population to double? All right, so we're talking about an exponential growth situation. So A equals P e to the RT power. Okay. Just a second. Check something here. Okay. Now, let's see if I can write that E a little more legibly. Maybe, maybe not. Okay. Let's get rid of that little picky, I know. All right, back to the problem. Let's see, if the current 8.2% annual increase in population remains constant, so R is 8.2%, which is 0.082, and that's annual, so that's per year. How long will it take, so time is the unknown, for the population to double? Well, there's a problem here. They didn't tell us what the population was. All they told us was that how long is it going to take for the population to double? Well, consider this. let's just call the beginning population that we don't know, let's just call it P, okay? Standing for some population. The ending amount is double that. So wouldn't the ending amount be 2P, twice P? Okay, let's see if we can solve the problem not actually knowing the initial population. All right, so using this formula, we're going to substitute 2P in the place of A. So 2P equals PE to the, and then our exponent 0.082 times T. So 2P equals P times e to the 0.082 T power. We're trying to solve for T. T is in the exponent spot. So to get there, we're going to have to change this to a logarithmic equation. But we can't do that yet. To play baseball, as it were, to switch forms, we need a number equals a base to a power. So that P that's in front is kind of in the way of our conversion. So we have to get rid of it. So we're going to divide both sides by P. When we do that, notice that P disappears. So it really didn't matter what the population was because it's not involved in the actual final calculations because we divided both sides by it. All right, now we can change this into logarithmic form. It's going to be log base e of 2 equals 0.082 t. But isn't log base e just natural log? So this is the natural log of 2 equals 0.082 times t. Now, to solve for t, we'll divide both sides by 0.082. So t equals the natural log of 2 over 0.082. And let's go to the calculator and see what we get there. Okay, so natural log of 2, close it up, divided by 0.082. And we get, let's see here, 8.45301439.7. They rounded to the nearest tenth of a year, so the 4 would be the 10th spot and the 5 would round up. So the time is approximately 8.5 years. All right. Now, take a look at the final thing we put into the calculator, which is this right there. Okay. 0.082. What is that? That's R. So it seems to me that T is the natural log of 2 over R. And in fact, it is. In fact, that's a shortcut formula for finding the doubling time of something that is growing continuously. All right. Let's take a look at another example. It says doubling money. How long will it take $1,000 to double if it is invested at an annual rate of 5% compounded continuously? So again, we're going to use that formula. Okay. Let's see, what do we know? We know that the starting amount is $1,000. How long will it take $1,000 to double? Oh, so the ending amount is going to be $2,000. If it is invested at an annual rate of 5%, 0.05, compounded continuously. So how long is it going to take? All right, so we've got $2,000 equals $1,000 times E raised to the 0.05 times T power. We're going to have to get rid of that $1,000 out front. So we'll divide both sides by $1,000. On the left side, we get 2. On the right side, we get E raised to the 0.05 T power. Well, let's see now. That changing that to exponential form, we get log base E of 2 is 0.05 T. That is, the natural log of 2 is 0.05 T. Dividing both sides by 0.05, we get t equals the natural log of 2 over 0.05. And on the calculator, the natural log of 2, close it up, divided by 0.05. And we get 13.86294361. So rounding to the nearest tenth, we get approximately 13.9 years. Now, you might be sitting there going, but Mr. Mayo, you gave us a shortcut formula and you didn't even use it. You're right, I didn't, because I wanted to do one more example to show that we could have just come right in and said t equals the natural log of 2 over r. So t equals the natural log of 2 over r, which would have taken us straight there without all this extra work. Okay, so new formulas for this section: a equals pe to the rt, and t equals the natural log of 2 over r. I'm going to pause the recording. And so let's take a look at the graphing screen. And what I want to look at is we are going to graph f of x equals e to the x power. All right. So to do that, we're going to have to be able to get some values, e to some exponent power. Okay. So again, I'm going to use -3, -2, -1, 0, 1, 2, and 3. Now, I'm not going to get exact numbers. I'm just going to get approximate numbers, and I'm not even going to be consistent in how I round off, just because I want you to see. I mean, we're not going to get a super accurate picture using this. But so let's find f of -3. That's e to the -3 power. So on my calculator, second ln e to the -3 power, and I get 0.04978. Let's call that 0.05. So we'll round that to the 100th spot, okay? How about -2? F of -2 equals e to the -2 power. So e to the -2 power is 0.1353. Let's call that 0.14. So again, we'll round to the 100th place. Let's see. F of -1 is e to the -1 power. E to the -1 power is 0.367, so we'll call that 0.37. Okay. E to the f of 0 would be e to the 0 power, which is 1. F of 1 is e to the 1 power, which is approximately 2.72. F of 2 is e squared, and e squared is approximately 7.38. So 7.38, and then f of 3 e cubed is 20.085, so we'll call it 20.09. Okay, so I'm going to just sketch using those approximate values. Let's see, -3, really close to the x-axis. -2, we're up just a little bit. -1, a little bit more than a third. 0, 1. 1 is at 2.72. 2 goes up to 7.38, again approximate, and 3 goes up to 20, which is off the graph. All right, so if I were to graph 2 to the x and 3 to the x, this graph would lie between them, okay? But just keep in mind, e is not a variable. It's a number. It's used when we're dealing with continuous growth or decay, exponential growth or decay, and it's a little bit less than 3, just like pi is a little bit more than 3. All right, that's all I have for today. So
Tonight, we've got section 11.5. Tomorrow, we're going to finish up this chapter. We're going to look at one small concept in 11.6 and then 11.7. Thursday, we'll review for your chapter 11 test, which is on Friday. Monday, I'll come back during class time and we'll have a review for anybody that wants to review for your final exam, which is next Tuesday. So you've got a chapter 11 test coming up this Friday and a final exam coming up on Tuesday. All right. So we'll see you later.